So the big picture for this lesson is population growth. Now, a lot of times population growth is simply modeled using exponential growth. Reason being, it is a simple function to use and it can provide some interesting information about growth over time. And this can be used for investments very effectively, however, not so much for populations. The reason being is populations are constrained by the resources around them. Usually that includes the amount of food, water, land, that type of thing. So for general exponential growth, it's just ab to the x power, where b is the growth factor and a is the initial population, and x would be the amount of time. And when a population is small, it will fit the exponential growth model. But when the population gets big enough, what happens is the resources start to impact the rate of population growth. So in this mice example, assuming the mice are in a large area, population could be modeled through exponential growth. So in 3 months there would be 48 mice, and in 10 months there would be 6,144 mice. So what happens is populations have a carrying capacity. In other words, there's a maximum population size for each population depending on the resources available. And if you look, this green curve represents exponential growth, but this blue curve is more realistic as what happens. The growth rate increases for a while and then starts to decrease and eventually approaches the carrying capacity. And this is called logistic growth. And there's a formula for this. So the C is the carrying capacity, and the A and the B, those are other constants for the function that you'll see later. Okay, so here's a more detailed graph of logistic growth. So I want to point out the initial value of the population is 0 for the input, and then the carrying capacity divided by 1 plus A. So if you know the carrying capacity and the A value, you can calculate this point. Probably the most important part of the graph, aside from the carrying capacity, is the inflection point. That's the point of maximum growth. That's before the growth starts to decrease. Notice that the population size, C over 2, this is half of the carrying capacity. So if you have a partial graph, in other words, you don't know what the carrying capacity is, if you can find the point of maximum growth, then you can actually estimate the carrying capacity pretty accurately. So disease spread can also be modeled using logistic growth. There's a flu example in the lesson, and in a population of 1,000 people, the carrying capacity for the flu is 1,000 because eventually everyone would get it, is the model here. In the beginning, no one in the population has the flu except for one person, so there are 999 people to spread the flu to. And then over time, as it spreads, more people spread it. And then eventually people who have the flu are interacting with people who already had it, so they're not going to be spreading it to those people, which is why the rate of spread starts to slow down as you reach the carrying capacity. So how do you find the number of days there will be so many cases of the flu? Well, what you can do is you can graph the logistic growth function and then graph as a second function the number of cases you're looking at, and the point of intersection, the x value, that tells you the number of days. So about 11 days is half the cases. And this is another trick to helping find the carrying capacity. So this 500 days, because it's half of the carrying capacity, it should be the point of maximum growth. So that's the big picture for this lesson, carrying capacity and population growth.